the vector autoregressive or VAR model contains multiple equations. The number of equations is equal to the number of endogenous variables in the VAR model. If we have k number of endogenous variables, then we can specify the VAR model using matrices as shown here. In the equation shown here, yt will be a k by 1 vector of endogenous variables. These are the dependent variables in each equation of the VAR model. Therefore, in a VAR with k endogenous variables, we have k number of equations with each endogenous variable as dependent in a separate equation. Upsilon is a k by 1 vector of constants or intercepts. Since we have k endogenous variables and k equations in the model, we will also have k intercepts in the model within the vector upsilon. The lags yt-1, yt-2, up to yt-ρ are all k by 1 vectors containing the lags of all the endogenous variables. As we can see, these are also the independent variables in each equation of the VAR model. The number of lags of y are determined by the lag length of the VAR model. Here, the lag length of the VAR model is represented by ρ. The matrices A1, A2, up to A ρ are k by k matrices of parameters associated with all the lags of the endogenous variables. The number of these matrices is equal to the lag length ρ because we have ρ number of lags of endogenous variables and we need the same number of parameters associated with them. For instance, the matrix A1 contains all the parameters associated with the first lag of endogenous variables. Finally, μt is a k by 1 vector of residuals, which are often referred to as innovations or shocks in the case of VAR models. Since we have k number of equations in the model, we also have k residuals in the model. The residuals of μt are assumed to be white noise, that is, they have a zero mean and constant variance. The variance-covariance of residuals is given by sigma and will be a k by k matrix. In equation 2, the diagonal elements of sigma are the variance of the residuals μ1, μ2 and up to μk. The off-diagonal elements all contain the covariances of the residuals of different equations of the VAR model. Under the assumption of time independence or no autocorrelation, the variances and covariances will be constant over time. As a result, we can express the sigma matrix as shown in equation 3. The diagonal elements are the variances, which will be constant because the residuals are white noise and not autocorrelated. The covariances of residuals will also be constant under the assumption of time independence. The interesting thing to note here is that the covariances of residuals in the sigma matrix will generally not be zero in a VAR model. That is, the residuals, shocks or innovations from different equations in a VAR model are generally correlated with each other. This further implies that there are contemporaneous effects and that certain endogenous variables affect each other in the same time period. If there are no contemporaneous effects, then the innovations of different equations will not be correlated. As a result, the covariances of residuals will also be zero in the sigma matrix in that case. In most cases, however, the VAR model residuals are correlated across equations, their covariance is not zero, and there are contemporaneous effects. This is also why we generally estimate the impulse response functions using structural VAR and structural shocks in order to incorporate contemporaneous effects of shocks. Suppose we have k equals 2 endogenous variables x and z and we are considering a lag length of 3 or ρ equals 3 in a VAR model. Then, we can specify the VAR model as shown here in equation 4. We will have two equations in the VAR model because k equals 2. Also, yt will be a 2 by 1 vector containing xt and zt as dependent variables. Since ρ equals 3, we will have 3 lags of endogenous variables as independent variables in each equation. We can see this in the equation as we have yt-1, yt-2, and yt-3 each containing lags of xt and zt. Similarly, we will have 3 matrices of parameters A1, A2, and A3. These will be k by k matrices, that is, 2 by 2 matrices of parameters. upsilon is a 2 by 1 vector of constants or intercepts, and mu t is a 2 by 1 vector of innovations or shocks. We can expand this equation 4 in the matrix form as shown in equation 5. This VAR model has two equations, and both equations are contained within this specification. We can also write this VAR-3 model using separate equations instead of the matrix form as shown in equation 6. In this equation form, we can clearly see which parameters belong in which equation of the VAR model. We have specified the coefficients of the A matrices in a format identifying the variable, equation, and the lag. For instance, alpha x11 implies that this coefficient is associated with x in the first equation and the first lag of x. Similarly, alpha z23 is the coefficient associated with variable z in the second equation and the third lag of z. Upsilon 1 and upsilon 2 are the intercepts of the first and second equation respectively. Mu1t and mu2t are the innovations of the first and second equation of the VAR model. The innovations are assumed to be white noise with zero mean, constant variance, and no autocorrelation. The Variance-Covariance Matrix of Residuals sigma is a K by K matrix. Hence, it will be a 2 by 2 matrix in our example of VAR-3 with K equals 2 endogenous variables. The matrix sigma can be expressed as shown in equation 7. The diagonal elements of sigma will be the variance of mu1t and mu2t. The off-diagonal elements will be the covariance of mu1t and mu2t. As discussed earlier, these shocks mu1t and mu2t will generally be correlated in a VAR model, that is, the off-diagonal elements showing the covariance of mu1 and mu2 will not be zero in most cases. This also implies contemporaneous effects between the variables x and z. Although we do not include contemporaneous effects in a VAR model, we can incorporate those in a structural VAR model, and we mostly include those contemporaneous effects while estimating the impulse response functions after VAR. VAR model also allows us to include deterministic terms and exogenous variables. Earlier, we specified a VAR model which included only a constant or intercept along with the lags. If needed, we can easily include a trend component or dummy variables for seasonal adjustment. Furthermore, we can incorporate exogenous variables along with the deterministic terms. In the equation 8 shown here, we have a VAR model with k endogenous variables, rho lags, and m exogenous variables. The dependent variables in yt, independent variables in yt-1, yt-2, up to yt-rho, and the A matrices stay the same as before. The vector et contains all the exogenous variables and will be am by one vector. The matrix gamma1 is a k by m matrix of parameters associated with all the exogenous variables in all the equations of the VAR model. The deterministic terms are included in the vector dt along with its associated parameters in gamma 0. The dimensions of dt will depend on the deterministic components we decide to include in the VAR model. These could be a trend component or seasonal dummies, which will be determined by the format of dataset or the structure of trend and seasonality. The equations in the system of the VAR model can be estimated one by one using OLS. This is because the independent variables may include previous lags, deterministic terms, or exogenous variables, all of which are predetermined variables. The estimates will be consistent and asymptotically efficient with white noise serially uncorrelated errors, even though the errors or innovations are generally correlated across equations. Generally, we apply the VAR model with stationary variables. If the variables are non-stationary, we generally do not apply VAR model because the impulse responses do not converge with non-stationary variables and the forecasts may be severely affected. In such cases, we may consider taking differences and estimating a VAR in differences or a VECM model if the variables are I1 and cointegrated. Thank you for watching, and I will see you in the next tutorial.